Okay, so if you click on this video, you're probably doing a titration lab, and you have no idea what you're doing. Or you could just be nervous about doing this lab, working the acids and bases, right? Could be kind of dangerous. So in this video, we're going to walk through what to expect on your titration lab, how it works, and the math behind it. So let's first start off with the lab portion. How are we going to do the lab? How are we going to do the lab? Well, there's some components that we have to know first. Typically, we're going to have a Erlenmeyer flask or a beaker. The Erlenmeyer flask looks something like this. The beaker, like this. So again, this is going to be our flask. This one right here is our beaker. We're also going to have a burette. Burette's going to be this very long looking thing. And on a burette, we have something called a stopcock. Get all of your laughs out now. Okay, and this is our burette. On our burette, there should be some lines indicating the milliliters. The last thing we're going to need to get is our acid and base, and I'll color code those. Let's make our acid red. And we'll make our base blue. Okay. So what are we going to be doing in this lab? Well, we're going to use our burette, and we're going to pour in some volume of either an acid or a base into a flask with an acid or base, and we're going to determine how much of the item in the burette that we needed to neutralize what's in the flask. To make it easier, let's do an example, right? So let's say in the flask, let's say I have an acid in the flask. So my red for acid, right? So here's my acid in the flask. My burette then should have a base. What's going to happen is when I open up the stopcock, some volume of base will go into the acid. Eventually, our flask will change color. Let's say we'll turn white here, and we will stop our titration. As simple as that. The hard part here is not overshooting, in this case, the amount of base that we add. And we'll explain why in a little bit. But of course, we can do the opposite way as well. I can have a flask where inside is a base, and in my burette is my acid. It's the same exact idea, where eventually we'll add some volume of our acid so that our solution will change color, effectively neutralizing whatever is in there. That's essentially what we'll be doing in this lab. You'll either be given, or you have to make, some concentration that goes into the burette, whether it's an acid or a base. And then in our beaker or our flask, we'll have the opposite thing. And you have to figure out how much volume we have to add to the flask to neutralize it. So the last thing we need to be wary of is our starting and ending milliliters in our burette. If we can get all of those, titration labs will be easy. Depending on the technology used, you may or may not get a titration curve. So let's talk about titration curves. if you're in a high school class, you probably won't get these curves. But if you're in a college class, or maybe even a well-funded high schooler, you might have what we call pH probes. And those can measure the pH. And those can measure the pH at any point in our titration. And those result in curves, so we can graph them to get our curves. What those look like depends on what's in our flask to start off with. If we start off with an acid, what we'll see for our titration curve, don't forget to label, right? So this should be pH. This is milliliters of base added. We should see a curve that looks something like this here. Similarly, we can do one for a base. But it'll kind of be swapped. We have something like that. On these titration curves, there'll be some key points. There'll be one key point that we call the equivalence point. I'm going to abbreviate that to EQ. So equivalence point is when our moles of acid and base are equal. The moles of acid and the base are equal. Sometimes that pH will be 7. It's only the case when it's a strong acid, strong base titration. Okay, so EQ equals 7 when strong base plus strong acid. Well, that means if it's not the case, our pH will not be 7. And you're probably wondering, why? Well, let's look at a practice problem, and we can see mathematically why it won't be 7. So let's look at this problem here. Let's look at a CH3 CO2H plus NaOH. So this is our strong base there. What's that going to yield us? Well, we should expect, so weak acid, strong base reaction. We can expect water plus CH3 CO2 minus plus a Na plus, but in our case here, we can ignore that Na plus. So in our example, let's say we start off with 0.1 molar with 25 milliliters of our acid. Let's say with the same amount of our base, 0.1 molar, 25 mLs. What's going to happen here? Well, firstly, this reaction is not going to be in equilibrium. If you notice, I say yields for a reason, because this is going to be a reaction that goes to completion. We talked about buffer solutions before in the last video. If you want, you can go to that one, and I kind of discussed why exactly there. But essentially here, because we have a strong base that associates 100%, therefore 100% of our base will react with any acid we have. So this first reaction will go to completion. So now this is a limiting reagent type problem. How we do that is we compare moles with moles. So to get the moles here, and we can go from there. So to get moles, 0.1 molar times 0.025. Same for both of them. That's going to give us 0.0025 for both of them. And we know both of them react completely. And we also know that they have the same amount of moles. It's a 1-to-1 molar ratio. Therefore, 1 mole needs to react with 1 mole. So therefore, we have equal amounts here, which means that we create the same amount of our conjugate base, or our CH3CO2 minus. So I'm wondering, okay, what do we do with these numbers now? Well, if we created all that and we reacted completely all our acid in our base, what can we do here? Well, guess what here? We have a molecule here, some concentration. Well, let's set up in an icebox. So we know then, in the solution that CH3, CO2 minus plus water will be in equilibrium with CH3, CO2H plus OH minus. And you see how we kind of have what we had above here, but kind of opposite. If you know, we start off with 0.0025 of our base in this case. And let me give you the Ka value here. And that's going to be 1.8 times 10 to the negative 5. Is there a way we can figure out the pH of this problem? Well, there is. If you want, pause the video here and give it a try. But this is, again, a very basic icebox that we can do. I'm going to scroll down here to give myself a little more space. But let's go for it. So first thing we should realize here is that we actually have the base form. So we need to get Kb instead of Ka. Kw is equal to Ka times Kb. Therefore, Kw over Ka is equal to Kb, which means 1 times 10 to the negative 14 all over 1.8 times 10 to the negative 5 should give us Kb. Kb is then equal to 5.55 times 10 to the negative 10. Okay, so there's our Kb value. Let me box that. Okay, so let's go back to our icebox now. Well, we have 0.0025 mole here. And if you go back up, right, we had 25 mils of our acid, 25 moles of our base. To get this into then molarity, we need to divide by our total solution, which we're going to divide this by 0.050 to get 0.05. So now we can do our icebox. So let me move this to the side here. I'll bring you up. Okay, so let's do our icebox now. We don't care about water. 0, 0. This is minus x plus x plus x. Equilibrium will be 0.05 minus x, x, which means our Kb expression is equal to our products over reactants. So it will be x times x over 0.05 minus x. Well, because Kb is smaller than 1, 0.05 minus x, the same thing as saying 0.05, which means then Kb is equal to x squared over 0.05. We know the Kb value here, so plug that in here and solve for x. So if you move this down a little bit, we can say that 5.55 times 10 to the negative 10 is equal to x squared over 0.05. Therefore, x is equal to 5.55 times 10 to the negative 10 times 0.05, all under a square root. By doing so, we should get that x is equal to 5.27 times 10 to the negative 6. If you see here, that x value has to be our amount of OH minus, which means we can use this to figure out pH. There's going to be two ways. We can use our Kw expression again and say that Kw is equal to the concentration of OH minus times concentration of H plus. Go from there. Or the way I find easier is to go to POH and then get pH. So let's scroll down a little bit. So we know that POH is equal to the negative log of OH, which is the negative log of X, which then gives us 5.278, which means pH is equal to 14 minus 5.278, which equals 8.7218. We can just round this here to 8.72. So let's look back. We made this scenario where a weak acid reacts with a strong base. We got it to a point where the moles are equal. But because our weak acid is in equilibrium with its base component, we actually got a pH that is not 7. So that's how it works mathematically. We can also just say that if we have a strong base, then our equivalence point pH will be basic. Or if we have a strong acid, then our equivalence point pH will be acidic. So two more things we wanted to cover today. The one is going to be Henderson-Hasselbalch equation. That is that pH is equal to pKa plus the log of A minus over HA. And this is just saying our base over our acid. And this is really useful because what happens when our acid and base are equal? I should specify this is a conjugate base. Well, what happens when these two are equal? Well, let's just give some random numbers out. Let's say that we have our pH equal to 3, and let's say our log part here is the same. So we have 3 equals to pKa plus the log of, let's say, just 2 over 2. Well, that's just 1. Log of 1 is 0. So this whole thing cancels out. So that means that pH is equal to pKa when our acid or base equals to our conjugate acid / conjugate base. We call this moment the half equivalence point. This is the half EQ point. So graphically speaking, if I were to recreate our titration curve, and if I were to say that right here, let's say this is a pH of 9 is EQ. That means when our pH is 4.5, that's our half equivalence point. We can also see that when we talk about the milliliters as well. If this was at 50 milliliters, the half equivalence point should be at 25 mils, and the same thing should be true. We should see that being a 4.5 pH. The last thing we want to talk about here is acid-base indicators. How do we choose a good acid-base indicator? It's going to follow what we did in Henderson-Hasselbalch. Essentially what's happening, let's scroll down here. Our indicator has two forms. It has its acid and its conjugate base form. Or you can have a base in conjugate acid form. But either way, it will play out the same. What's going to happen is that in one form, it will be one color or colorless. In the other form, it will be another color. So essentially what we want then is you want to hit right at that point where we have equal concentrations of both forms. If you go back to Henderson-Hasselbalch, and when our acid and base form are equal, we'll call that the half equivalence point. So what that means for us then, what that means for us is that we want the indicators pKa to be around the pH at the equivalence point. That's going to be it for today's video. Hopefully this helps you get a good understanding of titrations and kind of some of the math involved there. If you liked the video, please give it a like. Comment on any other topics you want me to cover. Thank you.